So in the previous segment we discussed about how to derive the wave equation in two different ways, and we saw also that those different ways gave us two different perspectives of the same thing. Okay? So you should always remember them. Even the meaning of the partial derivatives or the split equations, the partial of f with respect to t is minus c times partial of f with respect to x. So that meaning also is very important, you should always keep that in mind. Now what we will do is we will try to see what sort of form these f can take. We just said that our now xt can be something of this type, right? Say x, should I write like this or no? It should not be like this, isn't it? I should actually write like it's a function of so what should I use the symbol here? Let me write y. So y is the displacement from the equilibrium of the string, which will be a function of its distance from some origin x and time t. Both are the variable, and that will come out to be f of say x minus ct plus some f times x plus ct. So that is what we have come up to, and we said that this is the solution to the equation that fine. So that's what is we have come up to. But then the question comes, yes, it is true that any form will do, but then it depends on what? Any form will do, but in practical situation it must be depending on something, right? So the first thing which should be coming to our mind is it depends on how we start the system, right? Because if you compare with the 2 degree of freedom system, the solution is a combination of how we started, right? So that will decide about what type of motion will be contained in that general motion. So exactly in the same way here, the specific forms of f and small f will depend on how we start the system or the initial conditions. Okay. Now again this is a second order differential equation, so obviously again the similar way, either we can give displacements or velocities as initial conditions. You can now correlate with why they are the only ways to give initial conditions from the beginning of the classes, okay, from the single degree of freedom system. So those are the only two constants which we always, if we fix them, everything else gets fixed, okay. And yeah, so it will be, there is some other explanation also, but it will just get diverted, forget it. So now let us say we have this kind of a function which gives us how we start the system displacement wise, right. At that time we were saying that x naught was the displacement. Here it has to be a function because the string can be displaced in a particular way and we can start like that. So that displacement function is this, and along with that there can be another v naught of x with which we can start it, right. So what this thing means? That means at every location we are actually defining a velocity. Every location in the sense for every x, whatever x it is, wherever we define the coordinate system, say this is the origin and from here we define x. So for every x we will have to say something, and it tells me that at that point what is the velocity with which I started, and I can always give a combination of both. Again, always try to correlate with the single degree of freedom system so that it will be clearer. We are doing nothing more than just the single freedom system. We have extended it to continuous system. All the words that we were using are exactly the same now of what we are using. Okay. But then how will this imposition affect these things is the question, okay, which we are trying to answer. And for simplicity, there we were having a single mass system for simplicity. Here we have removed complexities by removing the end conditions. We are still we are considering only an infinite string. We never told that somewhere it has got stuck or something, right? So that we have done intentionally so that things will be under control, difficulty level, okay. Slowly we will remove those simplicities by putting boundaries. Okay. Now if this is an infinite string and we start with some function like this, what would be the shape of them? See, let's first, this is difficult anyways, velocity condition. So let's start with this, easier to tackle. So if I give a particular shape, maybe, right, like this. Now because there are no end conditions anywhere now, the string here doesn't have any bias for any direction, right? To start with, even when we have boundaries, the string doesn't, unless until this disturbances reach the end and come back, this point of the string do not have any means to know what will happen there, right? When it starts. Agree, na? So that is why whatever you give, it will just split into two parts and starts moving in two directions. Say something, want to say something? Okay. So that means half of y naught x will start moving in the positive direction or rightward, and half of that will move in leftward. Okay. Now if this is the shape which will start moving rightward, how do we convert this into moving wave? We will just change it to minus ct, right? So this is the part which has come from here, from the initial condition of displacement, but we will start moving rightward, and exactly in the same way, plus half y naught x plus ct. Agreed? So that's how, in fact, so suppose this is the solution for the transverse wave equation with the given initial condition, when the initial condition is like this. Okay. Now what?
Sir, can you repeat what you just told?
Okay. The last sentence?
Yes, sir, last.
I said that this is the solution of the wave equation with initial condition of this. Okay. So I have a wave equation defined on an infinite string, that is important, infinite string, on which I specified a displacement initial condition like this. Then the solution is this. But this sentence I don't like to talk about this. The solution of this differential equation is this. It means that the shape which I gave, it just got split into two parts. One part moved rightward, one part moved leftward. So this is what is the meaning of this sentence. I would like to see that so that it's clear. But yeah, so mathematically the English gets translated into maths like this. Okay. Then what? Now what about this V naught x? So this part is clear. Now if I want to give velocity initial conditions, what do I do? So what I do is, it's a bit involved because velocities are more difficult to analyze. If you remember the single degree of freedom system also, that was more difficult to analyze than the displacement, because you have to take the differentiation and do that. Now here, what we will do is, we will define another function, say S, to be the argument, I am skipping some space here, to be integral of the whatever V naught you have as a function. And again I emphasize this, that try to visualize what V naught x is. It is the velocity at every location that you have imparted. You go to an x, that's the velocity at that location. Okay, that means if I have now suppose now this is my V naught x, which means that at this point velocity is maximum, and this point velocity is low, at this point velocity is almost zero velocity. Okay, and it is the shape of the velocity profile. Now what you do, take the velocity profile and integrate it, say I'll write some other function because x will like this, and 0 to say z, and you will get obviously a function of z. Right? Now just try to see that here I could have used x also, doesn't matter, but I just I don't like to use x here because V naught x is defined on the actual domain. Now I am creating an artificial function by using the same function. So I am using a different independent variable to integrate it, and I am integrating it from 0 to z, and the function which I get is called sz. For now you just think that okay, I have just invented a function. I didn't. D'Alembert had invented this function. So that's why you have read this method to be the D'Alembert's wave equation. Okay. Now once you get this, what help it gives you? See, then now think about a function, say y of x of t, which looks like, suppose, and then now you think that this you take as a displacement. Whatever function you got it now, this is a function now. You consider this to be a displacement type. Then if you start thinking it to be a displacement type, you know what to do. You will split into two parts. So you will do one half of s of z, and the other part is again s of z, but one half will move rightward, so I will put minus ct, and one half will move leftward, so I'll put ct. But because this is not exactly a displacement initial condition, some extra things needs to be done, because so that extra thing is, here a minus 1 over c comes, and here a plus 1 over c comes, because they are the time dependence coefficient in a way. Okay. So he just invented that if you take this, he gave it. Now this will be a solution to this differential equation with this initial condition. You get this. So again I am in a way repeating. Suppose you have this velocity initial condition function. What do? You take it, do this exercise, you get a function. Okay. Now that function you split in this way with this coefficient, additional coefficient, and that will give you the solution of your problem on the infinite string. Now you can just check that why it works. Why it would work? See, the velocity is what? When you take partial of this with time, right? So at any location, the velocity will be given by the partial of this. If you do that, what would you get? Should I do it here or?
Sir, like, shouldn't it be x minus ct?
Okay. Yeah. So thanks. So yeah. So z has, I wanted to write that, but then yeah. Thank you. So this should be what's happening. Okay.
So this is like telling in single DO system we divided by omega to convert it into a kind of displacement condition, right? So whatever velocity initial condition we had.
Yes.
Kind
It's very similar to that. Okay. So when you you figured out the constant, you had this velocity over omega sort of thing. Yeah. So this is similar to that. So in fact, yeah. So here, so z has been substituted with x minus ct. Now, so yeah, this I don't want. So can you do yourself? I am also doing it here. So you calculate partial of I with t. It will be what? So this c will just get cancelled out. So you will have 1 over this undoing thing, 1 over 2 s of x minus ct plus half s of x plus ct. Right? So then or did I miss something? I missed, right? So I have to, these are partials with respect to the argument. Then see, do I have to say that? I'll just write it here. S prime, this is, ds over dz. Whatever is the argument, you take the differentiation with respect to the complete argument. So that's what is S prime. That is how, how do you differentiate it? First with respect to argument, and then this minus c is coming and getting cancelled. Okay. So this is what is the thing. So that means this is nothing but S prime x minus ct. But at t equal to 0, this is nothing but S prime of x. Right? Because see, this is valid for all time to come. For any time, this is valid. Because we have, this is the solution. We have said that we are just now checking that our claim that this is the solution is valid or not. Okay. So assume that this is a solution. Then we are trying to see what is the velocity profile for any time. So we just took the partial of that with respect to time. So we got it. So it is again valid for any time to come. But then we saw that this happens to be this. But now we are trying to see at t equal to 0 what will be its profile. So you just put t equal to 0, you get this. But now what is S prime with z? It is v naught, right? So that's what you get it. Is nothing but v naught of x. Right? So what did we prove? That whatever D'Alembert gave us to be the solution, it gives us back that, okay, when we moved back in time, we reached the same velocity profile where we started with. Okay. So in summary, now you know that if you have this transverse wave equation, so on an infinite string with initial conditions to be y, okay, I'll write it properly now. So x at 0 is y naught of x and partial of y t at t is equal to 0 is v naught of x. So these are the two initial conditions. Then my solution is equal to half y naught of x minus ct plus half y naught x plus ct minus 1 by 2c s x minus ct plus by 2c s x plus ct, where s z is equal to integral of v naught u du from 0 to z. Okay. So this is the full story that we discussed in the last 25 minutes as the solution of wave equation on an infinite string. Okay. Okay. So we'll stop here for this segment. I missed a bracket here. Okay. See you in the next segment.